Okay, we got diagonal matrices. Can anybody guess by looking at these matrices here, what is meant by a diagonal matrix? Has anybody been reading?
The only entries are in the main diagonal.
The what?
The only entries on the matrix are basically on the main diagonal.
Yeah, the only non-zero entries are along the main diagonal. So everything else is zeros. So here you have your diagonal. And then everything outside the diagonal is going to be all zeros. However, you did notice something interesting. What did you notice? On the third one, there is a zero in the diagonal. That is going to come into play. So it's good that you're noticing these things. So as an engineer, you want to be observant. So this third one here on the book has actually a zero in its diagonal. Now, what do you also notice about all of these? You should immediately see some other property. They're all square. Only your squares. Matrices are going to be categorized as diagonal matrices. Okay, so here are some other operations that you are going to be aware of. So here, this is just the general notation for your diagonal matrix that you have. Here, this one says, what does this say? This second statement, this is going to be very important. What does this statement here say?
We're
gonna practice reading. What does it say?
Diagonal matrix is invertible if and only if all of its diagonal entries are non-zero. In this case, the inverse of 1 is.
Yeah. So this is a very key statement. You kind of glance at it, and you're like, oh, I can skim all this. It just told you two very important things. It says a diagonal matrix is invertible if and only if all of its diagonal entries are non-zero. What can you tell me about those top matrices then? What's the first one? Invertible?
The third one is the only one that's not.
Third one's the only one? Which ones?
3 and 4, because you count 1.
Yeah. So this one, immediately you should see this zero in the diagonal. It is not invertible. Now, how do you connect that to a theorem we just went over? Remember your equivalent theorems? Now what do you know?
It's non-true.
That means all those other things, because it's not invertible, that means all those other things are false now. So it means now you won't just have the trivial solution. Now it means now you won't have whatever the rest of the statements are. So now you have some other things to work with. So you got to be able to use that equivalent statement theorem by some very key properties. So you kind of see how this is working? Okay, so if though, there's a lot packed into this one short sentence, but if it is invertible, then the inverse of D is simply 1 over whatever your entries were. So here's your D. If it's invertible, you can quickly find the inverse of a diagonal matrices by having each of these entries be 1 over whatever the original entry was. So that's a real quick manipulation there. Okay, so then the other thing is you can also do the power of diagonal matrices. So if you have a diagonal matrix that's raised to a power, all you got to do is take the entries along the diagonal and raise those to the same power. So this, what would need to be your very first thing you need to ask yourself before you do any of these operations?
Is it a square matrix?
Is it a square matrix? Because only square matrices are going to have these diagonals or be able to be diagonal matrices, right? And then what are you going to ask yourself?
All the values of the main diagonal, not 0.
Right. And that was going to tell if they are, then what? It means it's invertible. It means you can go back and look at your theorems and have all those equivalent statements. It also means now that you can easily find the inverse. Also means that you can raise the diagonal matrix to a power. So just realize that. Okay, so okay. All right, we did that. Okay. Okay, what do we want to do? We did the power, we're good. Okay, so inverses and powers of diagonal matrices. So let's practice that. What do we know about A?
It's a square matrix.
The square matrix.
It's invertible.
It's invertible. So now we can immediately find the inverse, right? So how do we find the inverse?
It's a reciprocal.
Yeah, it's reciprocal of each original entry in the matrix A. So 1 over 1, 1 over -3, 1 over 2. Okay, what else can we do? You can raise it to a power now. So here we have 1 to the 5th power. Here we have -3 to the 5th power. Here we have 2 to the 5th power. And then same deal with negative powers. So you got all that jazz going on. How did we achieve this one?
Came to the 5 and inverted.
What did we pull out first?
First thing Bert did, and we.
Yeah, you pull out the inverse, and then you raise the this inverse to the 5th power.
Can't you just do A5? A to 5 and just inverse that?
Or yeah,
Okay.
yeah. So that was a previous theorem we had in another section, right? So just remember, you got to remember your different theorems. So that's why I've put them on your different study guide. Okay, so here, this is another thing that you're going to want to take note of. Let's see. So here, there's matrix products that are easy to do that involve your diagonal matrices. What do you need to check first? This is remembering back to a previous section. If you can actually multiply them, right? So in this instance, you had to, this instance, the diagonal matrix comes in front so that you can actually do the multiplication. And then here, if you notice, what pattern do you notice here? There's a certain pattern here. So if this diagonal matrix comes first in the order, what can you easily do? Here, let me blow this up. You can see it. Yeah. So that means if you have diagonal matrix and this diagonal matrix is in the front position, you just take this D1 entry value and multiply it by all of the A entries here across the row. So you guys see that? D2, that's multiplied by all the row entries for row 2. D3 is going to be multiplied by all these third row entries. Now, this one where the diagonal matrix is in the second position, now what are you doing? Do you notice the pattern there? So now it's with the columns instead of the rows. So now D1 is multiplied by the whole first column. D2 is multiplied by the whole second column. D3 is multiplied by the whole third column. Yes.
How would we know like the difference? Like how would I, like if we wanted to put the D1 values in
The first or second order? Remember, what are our rules for matrix multiplication? The inside numbers need to match, and the dimensions of your product are the outside numbers. Right? So this one is a 4×3, right? And this one's a 3×3, so the inside numbers match. The only way they match is if this is in the secondary position, right?
Yeah. So
That's
like,
the only way you could take the product.
So why wouldn't I have like D1 across that
If-
first row? Like in the
When this is in the secondary position, all the D1s are multiplied down the column.
okay.
You can't have this diagonal matrix in the front because why? Because the inside numbers would be what?
Oh,
3×4,
so-
right? You can't do it. Okay? So you have to remember some of your other principles you learned earlier. Does everybody see that? Let's check online. Yes, Ryder made a good comment. Yeah, you can find the inverse pretty easily on this diagonal matrices. So, okay, so on to our next property here. So you're gonna want to pay attention to some of these things that I'm pointing out. If you don't believe me about this, you can go ahead and do all these row column multiplications out individually and you'll see that you get these. If you don't believe me about the pattern, you can actually go through and do it laboriously. That's good. Right, exactly. It's not as laborious as you think because, yeah, you're right, because they have all the zeros and that's why it works. Yep, exactly. So, kind of go through it slowly in your mind to show yourself why that is. Okay, so then we've got our triangular matrices. Now, once again, we're going to read this here. A square matrix in which all the entries above the main diagonal are 0 is called a lower triagonal. So what is one thing? What's the property about a triangular matrix? From that sentence? Square. Okay. Only these square matrices are going to have these nice diagonals. So basically, anything below this main diagonal, they all have to be 0 entries. So this would be an upper triangle. So you can see this upper triangle, right? Because all these lower entries are 0. This is a lower triangular matrices because all of the entries above the diagonal have zeros. So they've kind of shaded that in to show you, hey, this is an upper triangular matrix, this one's a lower. So just go ahead and look at that. Okay, so here I've got it as well on that side. So you can see where all these slides are coming from. Okay, so you have some couple properties that you're going to want to know. because these will be hint, hint, good, true, false questions, right? It says the transpose of a lower triangular matrix is upper triangular. And the transpose of an upper triangular matrix is a lower triangular. Yes.
Out of curiosity, what are some, like, I don't know, real life applications of triangular matrices?
Ooh, that's what I'm going to be giving extra credit for. So if you, I don't want to steal everybody's thunder, but if you really are curious about some of these things, you might want to volunteer.
I volunteer.
Yeah.
I'm just looking at
Yeah.
these types of matrices and thinking, why and how do people like come up with it?
I know, right?
But this is
Um,
one of the older, how would you say, isn't it linear algebra, one of the older?
Yes, it's one of the older maths.
It's like how they.
Um, Yeah. So yeah, it's really, really interesting, all these kind of things that they started noticing. But yeah, we can talk about that. For the sake of time for the exam, we won't go into too much, but remind me about that, okay? Or you could decide to volunteer. So up to you. Okay, so for this one, you want to make sure that you look through this theorem because here it says the transpose of a lower triangular matrix is an upper triangular. So who can remember what transpose is? Flip the rows and columns. So you should be able to kind of visualize that, right? Why it would flip. So you start off with an upper triangular, you do a transpose, it's now going to be lower, or vice versa. So if you want to go ahead and prove that to yourself if you want to, because you can see how these this row would now become a column. All these zeros would now be across the top. You can see how that would flip. Okay, so dun, 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 dun. All right. Whoop, was there something else I missed? Oops, yes, I missed some things here. Sorry. Okay, so here's some other things you want to pay attention to. We saw this already. Part C we talked about. A triangular matrix is invertible if and only if its diagonal entries are all non-zero. So we know that. So that's going to hold true for your triangular matrices as well. So your diagonal on matrices on either side of the diagonal are all zeros, but then you can also have these triangular matrices where that same thing holds true, where if the diagonal entries are all non-zero, that triangular matrix will also be invertible. So then you're going to be able to refer back to other theorems and have your equivalent statements, right? Here's another one. It says the product of a lower triangular matrices is lower triangular, and the product of upper triangular matrices is upper triangular. So if you have two upper triangular matrices multiplied by one another, they're going to end up in an upper triangular. If you have two lowers, it's going to end up, the product's going to be lower. These are pretty straightforward.
Upper triangular, that still be upper triangular.
No, this holds true for if you're talking about two triangulars. Might not always hold true in the other case. The inverse of an invertible lower triangular is lower triangular, and the inverse of an invertible upper triangular is upper triangular. So its inverses will have the same properties as well. So these are all good to look at for good true false questions, stuff like that. Okay. So what can you immediately tell me about A and B? They're both upper triangular, right? Which one is invertible? A, and why?
Because B has a 0.
Yeah, B has a 0 along the diagonal, so that one's not invertible. Only A is going to be useful to us in terms of those other theorem equivalent statements. Okay, so it tells you also that since A is invertible, then AB and BA must be upper triangular. So here's where you can go ahead and you can kind of confirm that for yourself. So here you have two upper triangulars. Their products are going to be also upper triangulars. So you're going to want to check that out. So here's the other thing too. If A was invertible, how did we get these numbers again? We determined that A was invertible because it's, yep, so it's a reciprocal of the entries. Okay, so we've got that. Okay, so one more concept here. Then we have symmetric matrices. So once again, we're talking about square matrices, and they're said to be symmetric if A equals its transpose. So I think that is pretty easy to see. So here's some examples. So these matrices are symmetric since it's equal to since it's equal to its own transpose. So you can kind of verify that. If you took the transpose of this, you get the same matrix, right? Now, what should you look for to be able to determine that? Can anybody figure out what you're looking for?
So
How could you immediately tell that these are symmetric? Yes.
look at the top from right to the bottom left,
Uh-huh.
and if those are the same
Mhm.
values,
So what you're looking for is you take the diagonal, is there a reflection across that diagonal? See how you take this diagonal? There's a reflection. Direct reflection across the diagonal. So you should be able to immediately look, hopefully look at those and say, hey, those are symmetric. But if you can't tell, then you can always take the transpose, right, and determine. Yes.
In this case of the symmetric, it means perpetuating the diagonal, but not the main diagonal, but rather the ones that you interchange when you do a transpose.
So what are we doing when we're doing a transpose? What are we doing?
So we keep the main diagonal, but we change the format, the one below we change with the.
We're interchanging our rows and our columns, right? Well, without me doing any work, if it's a symmetric matrix, then I already know that the transpose equals the original matrix. And the way that I was looking, very quickly glancing at these to look at that, is I was checking to see if there's reflection across the diagonal. So I wouldn't even need to do the work of like. So if they're symmetric, the transpose is going to be the same as the original matrix. So you should see a reflection across that diagonal. Now, keep in mind, what does this work for? Square matrices.